Welcome back. In this video, we're going to continue learning about the ideal gas law and bring in density as well. By taking measurements of a gas in a fixed volume, we can determine the identity of that gas. Early on in chemistry research, the balance was a very common tool used in many different experiments. By taking an empty flask that's been emptied out completely using vacuum and weighing it and then allowing a gas to enter into the flask, we can measure the gas that has entered into the flask. And then knowing that it has a fixed volume, we can determine its identity by looking at its density. So let's remind ourselves that density is defined as the mass of a substance per volume of that substance. We can also talk about mass in terms of the number of moles and the molar mass. And this is where we're going to see a relationship with the identity. Because we can relate mass to molar mass, and density to mass, we can use them to determine the identity of an unknown gas. So by combining the relationship between density and mass and volume and moles and mass and molar mass, we see that density is equal to the moles of a substance times the molar mass over the volume. Now, if we look at the ideal gas law, we can substitute in by solving for volume. If we rearrange the ideal gas law and obtain moles over volume on one side, that's equal to the pressure divided by the ideal gas constant and divided by the temperature. Because density is equal to the moles times molarity over volume, we can substitute this in, and we get that the molar mass of a gas is equal to its density times the ideal gas constant times the temperature in Kelvin over the pressure. Why don't you think about this problem? Which of these scenarios would decrease the density of a gas? Pause the video and think about this, and then I'll walk you through it. Welcome back. So how do we think about this? Well, we know that the density of an ideal gas is related to the molar mass times the pressure over the ideal gas law and the temperature. So if we want to decrease the density of the gas, and we're changing the pressure and or the temperature, that would require either a decrease in pressure or an increase in temperature, because temperature and density are inversely related. That means then, for our scenario, that we would have to increase the temperature in order to decrease the density of the gas. And hopefully this makes sense. Remember, when we looked at the relationship between temperature and volume, if we keep the pressure the same, but we increase the temperature, the gas is going to expand and it's going to occupy a larger volume. Therefore, for the same amount of gas particles, it's going to have a lower density. Let's take a look at another problem. What's the density of helium gas in grams per liter at 21 degrees Celsius and 752 torr? I've listed for you some conversions and constants and equations that might be useful. Pause the video and try this on your own. Welcome back. So in order to find the density, we need to determine the molar mass, pressure, and temperature. Molar mass of helium is just over 4 grams per mole. The temperature is 21 degrees Celsius. However, we need to convert to absolute temperature, so Kelvin. The pressure is given here in torr, and we could use the gas constant R that uses liters and torr, but since we've given the gas constant in terms of atmosphere, let's take the relationship between atmosphere and torr and convert. Now we're prepared to enter the values into this relationship. We have the molar mass, the pressure, the gas constant, and the temperature. And what we should see is that in order to obtain a density, and we want the units in grams per liter, everything else should be canceled out. So we have atmospheres in the numerator and the denominator. We have inverse moles in the numerator and inverse moles in the denominator. And then in the denominator, we have both Kelvin and inverse Kelvin. That leaves us then with grams per liter. And that's our density. Let's try another problem. We have a plot here, which is a Maxwell-Boltzmann distribution, as we've seen already. And these are different gases at the same temperature. If each of these gases were in a 1 liter box at STP, which would have the greatest density? Pause the video and think about this, and then come back and we'll talk about it. Welcome back. So since we're asking about density of a gas, we want to use the relationship between density, pressure, temperature, and molar mass. We know that density is proportional to molar mass, and therefore the densest gas will have the largest molar mass. As we've seen already as well, we know that the heavier the molecules at a given temperature, the lower the root mean square speed. That will tend to provide a distribution that is more narrow, but has a very high peak. So since we're looking for the molecules with the greatest density, we're looking for those with the greatest molar mass. And that would be the substance A. If we wanted to know which substance had the lowest density, that would be E. Here's one more problem for you. If you have an equal mass of each gas that's put into a separate balloon, which will have the greatest volume, assuming that they all have the same temperature and pressure? Pause the video and try and solve this one on your own first. Welcome back. So we want to know, how does the mass of the gas relate to the volume? Well, we know that there's a relationship between moles and volume, and that they are directly related. The greater number of moles, the greater the volume. We also know that there's a relationship between moles and the mass of a substance and the molar mass. Since each gas has the same mass, in order to evaluate the number of moles of each one, we would see that the larger molar mass would result in fewer number of moles. So all we need to do here is evaluate which molecule has a given molar mass. So by looking at the periodic table, we can determine their molar masses. And the largest molecule, the heaviest molecule, will have the fewest number of moles and therefore the smallest volume. So the substance with the smallest molar mass will have the greatest number of moles and therefore the largest volume. That's it for this video. Thanks for watching. Have a great day.